The first of the two new tools at SBN I've been working on pertain to Catch, which I have presented before. As a quick recap, Catch is the Comet Asteroid Telescopic Catalog Hunter, a recovery tool that allows you to find comets and asteroids in large catalogs by extrapolating their positions back in time using their orbital parameters. Here is version 4 of Catch at the live site, catch.astro.umd.edu. The presentation I gave before can be found on the About page in case you want to remind yourselves about how it works under the hood. So let's look for an object of interest such as 65p. And here we have the main dashboard for object 65p. You might be familiar with this dashboard. You can leaf through all 3,489 occasions at which Catch has attempted to locate 65p. You can filter on the various catalogs that we have. But now what's new is we have a shiny new button here called Catch Analysis Tools, or CAT for short. This will allow you to perform preliminary astrometric and photometric computations right here in the browser without having to download or script anything. So let's pick an object of interest and open the CAT Tools panel. This is experimental, of course. We will be looking to improve it in the months to come. And let's launch the workflow. The first stage in the workflow is to perform astrometric corrections to the image. For neat images, we sometimes have a systematic error in the world coordinate system. The API behind the CAT tools uses astrometry.net to detect stars in the image and compare their patterns to reference positions from Gaia. The predicted position of the object gives us our rough array and deck to look for such positions within Gaia. You can adjust these inputs and you can adjust the search radius. Astrometry.net then computes a revised pixel to sky transformation and returns a new FITS file containing the corrected world coordinate system. In this experimental stage, we also enable you to adjust other inputs to the underlying astrometry.net functions, but we might hide these in the future if we deem them to add negligible useful control to the researcher. So let's ping the API. This result came back fast because these precise inputs have been cached, but this might well take 30 seconds or so uncached. Once the corrected world coordinate system comes back, we can apply or remove these corrections. So now that we have applied the correction, we can see that the object is in fact located exactly pretty much where we predicted it to be. The inaccuracy was not from the orbital parameters, but the neat world coordinate system in this case. The next step in the CAT flow is to use the stars in the background to surmise something like the real world magnitudes of the pixels in this image. Let's run this. Here we can see which objects were detected and used for the calibration. And this graph shows the correction used to convert brightness measured from the image's pixels into a calibrated apparent magnitude. Because NEAT's filter response depends on an object's color, the conversion includes a color correction. This fit used pan stars, stars with known magnitudes, to determine the 0 point and color term applied to the target. The next step on our way to computing a calibrated apparent magnitude for this object is to identify something like the center of the object. We do this by specifying a pixel within the object, By default, this is the pixel corresponding to the predicted position of the object after the astrometric correction has been applied. The CAT API fits isophotes and curves to the surrounding pixels and returns a new central pixel along with this image. So here you can see the red arrow is where I clicked, and the little yellow dot is the computed center of this object, determined by applying isophotes and curves to this body of light. The next step in this workflow is to allow you to fit a crude shape about that central pixel to represent the object, as well as to represent the background. By default, this is a circle of adjustable radius to represent the object, and a surrounding annulus to represent the background. So here you can see this circle, the pixels inside will be used to compute the photometry of the object, and the annulus around it will be used to compute the background. The final step brings all of these inputs and outputs together into a final estimate of the apparent magnitude of the object so defined. For an object like 65p, I am told to put the value of 0.55 here. Please try out the workflow for yourselves. Send us feedback if you have suggestions for improvement. We will continue to work on it in the months to come, in particular to explore whether it is feasible or not to compute CAT results like this in bulk.